Greetings. In last lecture, we had a discussion on various methods of analyzing determinate frame, in which we have completed method of joints. Today we'll discuss about the method of section. To begin here with, let us move with a numerical with a statement. Determine the forces in the member FH, HG and GI in the truss shown in figure. Each panel load is 10 kN and all triangles are equilateral triangles with sides 4 meter. The given figure shows a 7-bay truss spanning about 28 meters. 7 multiplied by 4 meter, each bay length is given to us is 4 meter, and it is desired that we should find out what force is being attracted by member FH, the member HG and GI. For this, I will not go with the analysis of truss by joint method, because I am not interested about to know the forces in other joints. Simply, I am going to have estimation of the forces carried by these three joints, which has these three members which has been addressed here. So for that purpose, what I will do, I will pass a section through this member such that it bisects or cut all the members like FG, FH and HG and GI being cut by this section. And after doing so, passing the section, I will prepare a free body diagram for this portion which remains behind this section XX, and I will apply equilibrium equation to analyze the unknown forces attracted by the members. Let's begin with it. Let us have free body diagram first. I will consider the force FH member force is being compressive in nature, having a compressive force towards the joint F. Similarly, I will consider the force in member GI as a tensile force pulling the joint G here, and I will consider FGH as a force which is in compressive nature for the inclined member GH. As we know that for an equilateral triangle, the angle is about 60 degree, and the loading given to us for the truss is symmetrical one. Then by the symmetry we can say that RA is equals to RO. Both the end reactions will be of equal magnitude, which equals to 10 into 7 divided by 2. 7 panel points are there and panel load is 10. So 10 into 7 divided by 2, 35 kilonewton are the reactive forces which are being attracted by this truss. Now we'll apply static equilibrium equation for coplanar force system, summation of moment about G. So I am going to take a summation of the twist which has been caused by the forces at the joint G. The very first I have considered here FH, the force which is from member FH, and the twist caused by this is anti-clockwise movement FH into multiplied with the perpendicular distance with reference to the axis of rotation. So we know the sides of triangle only. The perpendicular distance can be found out with the trigonometric relation for the geometry given to us. From that we can get 4 into sine of 60 degree is nothing but the vertical intercept for that particular element. Now I will consider the other forces here, like the panel load at B. If I want to take a twist of it, it will be 10 into the perpendicular distance, which is 4 plus 4 plus 2. It will exactly pass from the half of the member AC. That's why 10 into 10 will be the twist caused by this force parallel load. Similarly, the panel load at D will cause a twist which is equals to 10 into 6 plus the panel load at F will cause a twist about 10 into 2. All these are going to have an anti-clockwise twist. That's why I'm putting them into a same sign. There's a positive sign, whereas a reactive force of 35 kilonewton magnitude will provide a twist which is clockwise in direction, and the perpendicular distance is 4 plus 4 plus 4, that is 12. I am putting it as a negative minus 35 into 12, and if I take a statics of this equation, I can find that FH means force in member FH is about 69.28 kilonewton compressive in nature. Now I will apply the equilibrium equation in vertical direction, where I will take the balance between vertical forces acting on the truss. So here very first component I consider is the FGH resolved component along y direction. Since I consider the angle is made with horizontal, the vertical component will be a sine component of it. So here I can say minus FGH sine of 60 degree, and why negative here sign, because it is going to be downward. Similarly, minus 10 panel load is going to be acting downward, minus 10 at D going acting downward, then 10 kilonewton at F minus 10 plus 35 the reactive force going upward. If I take the balance of this equation or static of this equation, I can get FGH is equals to 5.77 kilonewton, and that too in compressive nature. Now one equation remains with me, that is summation of force in x direction. So what I will do here, I will take a summation of all the forces which are along x direction. Very first one is FGI, which is going towards the right hand side. So I will consider it as a positive, minus FFH is going towards the left hand side. I am considering it as a negative, minus the component part of this inclined force FGS, the cos of 60 degree. I will put that value here. And we know FH value, we know GH value, we'll substitute the individual value, and what the result will get, FGI is equals to 72.16 kilonewton. Thus by applying section method, we can find out the force in any member at any place without going for the what we say cumbersome exercise of method of joints. So let us move towards the next part. Now I will discuss about the graphical method. Graphical method was developed by the force polygons drawn to a scale for each joints, and then the force in each members were measured from one of these polygons. Actually, this method is based on the polygon law of forces, where we can say the closing side of the polygon will represent the resultant, and how we prepare the polygon with reference to the vector and the space diagram. In the same sense, we are going to analyze the frame here. This method is adopted when very complex frame is given, or the frame is having truss is having number of members in it, and it's not possible for us to address all the forces with the help of method of joints or method of section. In that case, we are going to have polygon forces, where we'll prepare polygons of a scaled units, where we will convert the force into scale dimension, and then we are going to prepare the vector or space diagram from it, and then the number lines which have to be drawn can be greatly reduced. However, if the various forces polygons are superimposed, so then what we'll do, we will try to superimpose the common joints here, thereby reducing the number of lines to be read, and thereby it makes a easy task for us to find out forces in a complex geometry. The resulting diagram of truss is also known as Maxwell's diagram. Okay, I will not go in depth how to construct the space diagram, how to construct the vector diagram, how to scale up these things. Just a review. I am going to put these things in front of you. What I will do, I will put here the steps how to construct the solution with the help of graphical method. The procedure involves the following step. Number one, we are supposed to find out the reactive forces by applying available static equilibrium equations. After knowing the reactive forces, now we will go towards the formation of a polygons. For that, we will move clockwise over the outside of the truss and draw polygons to certain scale for the entire structure. Then what we are going to do in the next step, we are going to have one by one joint analysis by superimposing the common joints and by superimposing the polygons individual, to have at least two unknowns with us. Next one, I will measure the magnitude of each vectors which has been drawn there, and I will scale it with a scale factor which we consider for the analysis, and based on that I am going to predict what type of forces is being attracted by a particular member. And lastly, what I will do, I will have a sequential of the process in such a way that the end from where I have started, I will come close at the same end, so as to have the balance or check of the forces or members which we have started with the analysis. With this, we'll move further with a new topic known as the deflection of the determinate frames. Here I am interested to know determinate frames. Here I am interested to know what is the deflection observed by a frame under the applied loading. So let us consider a simple geometry here, which is to be your compound truss, and having a supports. One side it is being simply supported, other side it is having a roller support. I will consider the cross section area of this is subjected to a force F kilonewton, and cross section area of these members as a and this cross section of the members remain constant throughout the frame. There is no deviation in the cross section, or unequal sections I am not going to provide. And similarly, I will make an assumption here that modulus of elasticity of those members are constant, is there is no change in the modulus of elasticity. But beside this, I will assume that the member length are different, thereby the force attracted by the members will be different. Let us consider the force F is distributed along the member like F1, F2, F3, F4, F5, F6, F7. Since each member carries individual component parts of that applied force F, and due to this applied force, let us consider there is a deformation in the member, and this deformation in the member is being stored. Okay, if we consider individual deformation stored by the member, I can say individual strain energy possessed by the member, that is u1, u2, u3, u4, u5, u6, u7. If I have a summation of all this strain energy, I can say this is the total strain energy possessed by the truss here. So we know that the truss element is be subjected to a gradual loading. Okay, and due to the gradual loading, the member is axially either axially tension or axially compression. That's why we are knowing the relation for strain energy related to members which are subjected to gradual loading, which comes to be F1 square L1 divided by 2 AE. So if I want to know U1, I will write the equation likewise. F1 force attracted by the member, the length of that member divided by 2 into AE. AE I will consider it as a axial rigidity. Similarly, U2, if I want to write, I will write here U2 equals to F2 square L2 divided by 2 AE. Likewise, I can write individual equations for finding out individual strain energy stored by the member. If I want to write the equation for total system, then I can write UI is equals to summation of Fi whole square Li divided by 2 AE. It should be read as a U. Here Fi is indicates here the ith number of the joint under consideration. L indicates the ith number of length under consideration divided by 2 AE. 2 AE is here axial rigidity. Now, in the case of determinate trusses, we assume that there will be no effects of the temperature rise or fall or lack of fit. As the member of pin jointed, they are free to get expired and swell. There is no such a restriction. That's why they will not be subjected to any secondary stresses or additional stresses. Okay, while in case of indeterminate beam, we have to consider it. We'll see that in the case of indeterminate beam, indeterminate trusses, not beam, indeterminate trusses. Now, let's put the here I am interested into knowing the deflection caused due to the force F here, and we know that the force is being distributed along the members. When the force F tries to deflect the truss, all the member will have certain contribution towards the deflection. So we know that as per Castigliano theorem, we can write here the if I am interested to know the deflection at a particular by the particular load, what I can do, I have to take a partial derivative of the total energy stored by the system with reference to the load under which I want a deflection. This was a statement made by Castigliano. If I put ui is equals to 1 upon 2 AE, this constant I have taken in bracket, what remains summation of Fi square into Li square. So if I consider that force deflection under the loading is F is equals to dou U upon dou F. What I have done here, I have taken partial derivative of the strain energy possessed by the system divided by dou F is nothing but force under consideration for which I want to find out the deflection. Let's this deflection is represented by di bar. So I am interested to know what is the value of di bar here. Before that, I will make a statement here. Force in member is equals to K times the applied force. So here what I am going to have here, I am introducing that F is the force here. So here F1, F2, F3, F4. Likewise, the contribution is there. Means there is a certain proportionality between this, and I will say that proportional constant is here K. It is a K times. Let's say the member F5 attracts the force about 0.7 times of the total applied force. So then I will consider it as a K as a 0.7 here. So I have written these individual coefficients for it, and now I am interested to know what is the individual coefficient. For that, what I can do, I can have a equation, right? Dou U upon dou F is equals to 1 upon AE summation of Fi dou Fi upon dou F into Li. If I take derivative of this particular relation, then we will get K as a resultant. So we can write di by equals to summation of Fi Ki Li divided by AE, where K we will call it as a unit load factor. So here where Fi is the force in the member due to the load applied, F and Ki is the force in the member when a unit load is applied instead of a F. To know the value of this coefficient, I will apply here unit load, and if I apply unit load, what remains here derivative will be the constant here. With this I will end up the session.